In the land of my dreams, the wind blows cold and the cat is always happy. But these two states are orthogonal. Cold wind makes unhappy cats, and so heat must be made. In the land of my dreams, the making of heat is a continual, rhythmic cycle. The forest makes deadfall, the deadfall makes logs. The logs make firewood, the firewood makes happy cats. Forest, logs, wood, happiness. In the land of my dreams, the nature of happiness is transitive with respect to firewood. It's impossible to imbue one's cat with too much happiness, and transitively, impossible to create too much firewood. Therefore, happiness itself in this place varies directly as a function of my firewood making capabilities. Thus it's given that the land of my dreams requires the wood splitting apparatus of my dreams. Isotopicity describes the property of a given material to display similar mechanical properties along every dimension, length, width, and height. Materials that don't do this, that is, materials that display different mechanical characteristics along one dimension when compared with the other two, are called anisotropic. Cheddar cheese is isotropic, whereas string cheese is anisotropic. Tomatoes, isotropic. Celery, anisotropic. Dr. Strange, isotropic. Reed Richards, anisotropic. It is the anisotropicity of wood that makes splitting it possible, composed almost entirely of long, narrow tracheids, or fiber cells, that are oriented longitudinally along the trunk and branches. Wood grain possesses the common anisotropic trait of fracture vulnerability. Thus it's given the creation of the optimal wood splitting apparatus of my dreams requires a thorough understanding of the anisotropic properties of wood. The seminal paper on the subject is The Mechanics of Splitting Wood and the Design of Neolithic Woodworking Tools by Enos and Oliveira. Building upon the work of Euler, Riccati, Young, and others, the paper expands Young's modulus of elasticity into a mathematical model to describe the force required to impose radial fractures in logs. Their model is precise and makes several intuitive predictions. That the force required will rise to the power of 1/4 with Young's modulus E. This is intuitive. Denser wood is more difficult to split. That the force required increases as a function of the log's radius to the power of 7/4 is also intuitive. Larger rounds are more difficult to split. However, the model makes several progressively more unintuitive predictions. First, that the force required falls with the square root of the blade's insertion distance. This follows from measured published observations that the fracture length x will increase with the square root of the displacement of each cantilevered end, as the anisotropic weakness in the wood begins to work in our favor. Thus, we predict that the preponderant amount of force required to split a log is actually at the moment of impact, at which point a fracture is created and the requisite force drops rapidly as that fracture distance x increases. The paper then proposes an equation to account for the coefficient of friction working against the blade, where the blade is considered to be a triangular-shaped wedge with a given angle, theta. Because of the aforementioned observation that force decreases as a function of displacement, it can be mathematically shown that larger values of theta incur less frictional resistance, because more aggressive angles increase the displacement, deepening the fracture distance x in greater proportion to the blade depth. This rapid expansion of fracture distance undermines the cantilevered end's ability to impose friction upon the wedge, so we see the greater the proportion of x to blade depth, the smaller the friction force acting against the blade. The trade-off comes with the effective work of fracture at the moment of impact. With wider blades, more initial force is required to impose new fractures where x is 0. But given that extra amount of impact force, it can be seen that the overall energy required by a wider blade is less than that of a narrow blade. Thus, unintuitively, it's easier to move a wider blade through a block of wood than it is a narrower blade. The predictions made by the model are then tested empirically. Blade angles up to 40 degrees were measured, and the observations confirmed the predictive model. The widest angle blades available on commercial splitting mauls are also no larger than 40 degrees, and no published work considers blade angles wider than this standard. This is probably because the worst-case point of impact force required by very wide blades to impose a fracture in firewood-sized deadfall approaches 1400 newtons, which is beyond the force possible for a human to generate by swinging a maul. Competitive lumberjacks, for example, which I promise is a real thing, typically swing a 3 to 5 pound axe head at 80 miles an hour, or a 2 kilogram blade at 130 kilometers an hour, generating around 100 newtons of force at the point of impact. But the land of my dreams doesn't concern itself with the paltry limitation of competitive lumberjacks. Thus, the wood-splitting apparatus of my dreams will employ a 60-degree blade. Working backwards with the Enos Oliveira model, it can be seen a point of impact force of 2,000 newtons will sometimes be required to impose fractures in the 8 to 12 inch diameter rounds I typically work with. This force is roughly equivalent to a 100 pound blade traveling 100 miles an hour, or a 45 kilogram blade traveling 160 kilometers per hour. To achieve the desired weight, my design employs a large section of steel bar stock for the blade driver. Because the force of impact will be high, the blade itself was shaped directly into the material. This was accomplished by grinding out the corners of the bar stock, pounding two ends together with a sledgehammer, welding in a 1/4 inch bit, and then grinding to achieve the desired angle. Two smaller diameter lengths of bar stock were then welded to each side to act as swing arms and mounted off-center to a fulcrum, whose hinge was fabricated from the bar stock itself. This offset provides more weight forward of the fulcrum, which results in higher velocity downward swings. Finally, the angle of the blade relative to the swing arm is greater than 90 degrees to ensure that the blade squarely impacts the material on a downward swing. Now, to achieve the requisite blade velocity, a large, heavy-duty garage door spring is employed past the fulcrum, making it trivial for a human to raise the blade nearly vertically and achieve a rapid, rhythmic downward thrust, thus simulating the full-length swing of a paltry competitive lumberjack. Rapid downward force is further aided by the addition of this handle, which extends forward of the blade head and enables the operator to obtain optimal leverage at the moment of impact. Initial testing of the log splitting apparatus of my dreams strongly indicated that the design was sound and that the apparatus was clearly capable of generating the requisite force to split large diameter rounds. However, in practice, I find that a full speed swing is typically only required when the material exhibits some latitudinal reinforcement in the form of a knot or branch growth, lending some radial strength and increasing the Young's modulus of the material itself. In extreme cases, cross growth like this can render the material effectively isotropic, see Beeler 1996, but this phenomenon is fairly rare. And even in the case of lateral growth providing radial strength, I've found that several repeated half-speed strikes work more effectively to create a fracture than a single 2,000 Newton impact, which tends to cause splintering and potentially hazardous airborne splashback. And so it was that the log-splitting apparatus of my dreams brought happiness and warmth to the land of my dreams, liberating my cat from the confines of that one beam of sunlight that meanders slowly across the floor each morning, and eventually provoking my quest for the kindling-making apparatus of my dreams. But that is another story.